Morning, students. Today we will discuss the concepts of deadlock detection and how to detect a deadlock using some sort of algorithmic activities and how to recover from deadlock if a deadlock ultimately happens or exists in a particular system. So with that, we will start our discussion for today. So basically, as we have seen earlier, that there can be two different scenarios. In scenario one, we have only single instance of each resource, and other can be multiple instances of each resource. So if there are only single instances of each resource type, what we can do to detect a deadlock, we can maintain a wait for graph. What is that? We have seen the resource location graph earlier. Now, if we make that particular graph compact by removing all the resource nodes from that particular graph, then what we get is a shorter version or compact version of that particular scenario. Then we call them as a wait for graph. So here in the wait for graph, there are several nodes which are the process nodes, and they are being connected with directed arrows. For example, if pi arrow pj is there, then pi must be waiting for a resource that is held by pj at this point of time. So basically, using the wait for graph, we can periodically invoke a particular algorithm that will search for the existence of deadlock in the particular environment. Now, an algorithm to detect a cycle in the graph requires an order of n square operations, where n is the number of vertices in the particular graph. Now, while doing so, if there exists some sort of cycle in the graph, then we can say a particular deadlock has occurred. So, how the particular wait for graph looks? So, at the extreme left position, we can view a particular resource allocation graph, and the corresponding wait for graph is being shown here in the rightmost rightmost column. So you can easily see that the corresponding wait for graph is a particular compact version of the previous resource allocation graph, where we have removed the particular resource nodes from the graph, and we have converged the particular resource nodes by removing the resource nodes to only having the process nodes. So basically, a directed arrow from P1 to PG to P2 will only exist if PI currently requires a resource, say Rj, and that Rj must be allocated to P2 at the present point of time. That means we are basically making the graph more compact. That is the case here. Now, the other case can be several instances of each resource type. So in that case, what we can do, we have to modify, we have to keep in place certain data structures as we have seen earlier. So so they can be as follows. One is available. That's a vector of length m indicating the number of available resources of each type currently in the system. Allocation is a type of n by m matrix which is defining the number of resources of each type currently allocated to each of the processes. And request. So request is also a type of n by m matrix which indicates the current request of each process. So basically, if request ij equal to, that means process pi may request more instances of resource type rj in future. Now we will come to the detection algorithm part. So what are the steps in that particular algorithm? At the very beginning, we are considering two vectors, work and finish, having length m and n respectively. Now we are initializing them as follows. Initially, work equals to available. So here available actually denotes all the resources which are currently available. And for I, that is I is the index here. For I equal to 1 to n, as we are considering n number of processes. So if allocation of I not equal to 0, that means finish of I equal to false, that means the particular resource is currently been executing, and otherwise finish of I equal to true, that means the process has finished its execution. So in the second step, what we are doing, we are finding such an index I such that finish of I equal to false and request of I less than equal to work. Then only we can proceed, and then only we can proceed. And if that condition does not exist, then we have to go to step 4. Now in step 3, what we are doing, we are allocating work equal to what was allocation I. We are allocating the resources to a particular process, say pi. So we are assuming that after some time pi will finish, and it will release all its resources to the system again. So again we will go to step 2. So that will occur in a cyclic fashion. And ultimately in step 4, if finish of I equal to false for some I, say here I, so here I ranges from 1 to n, then the system is in the deadlock state. And moreover, if finish of I equal to false, then pi is deadlock. So what happens is there, so at the end, if finish of I equal to is false for some particular processes, then that particular process must be in the deadlock situation. And in the reverse case, if finish of I equal to true for all the I, then we can easily say that the particular system is in a safe state and all the processes will finish their execution without any sort of problem. A point to be noted here, that is the algorithm, the detection algorithm requires an order of m into n square operations to detect whether the system is in a deadlock state or not. Now we will see a particular illustrative example here of the detection algorithm. So basically, we are considering here five different processes P0 through P4, and there are three resource types A, B, and C having 7 instances, 2 instances, and 6 instances in total. At a particular time t0, we are getting the particular snapshot which we can see in the screen now. So basically, you can see that if you add up all the values in the A column for all the processes, it will come to 7. If you add all the values of all the columns, in for case of B, it will come to 2, and same for C also, it is 6. So basically, at the very left, we are having the allocation table. Then we are seeing, then we can do the request table, and ultimately, and last we are getting the available. So basically, at this point of time, available is 0 for all the resources, and we can see that the request of process P0 and P2 are nil. That means they don't require any more resources at all. So we can easily say that P0 and P2 can be finished initially without requiring any more resources for the time being. So we can get a sequence here. Now see what is the sequence here? P0, then P2. So after P0 and P2, when they will finish, they will release all their resources into the system. And with that particular resources at hand, we can easily finish the remaining processes of P3, P1, and P4. So in that way, this particular sequence will result in finish of I equal to true for all I. That means in this way, we can satisfy the demands of all the processes. Now remember one thing, the particular safe sequence, they can be multiple. That means we can have multiple safe sequences. Now in the screen you can see a particular sequence there. In the same way, you may be having more than one safe sequence also. That will not pose a problem for you. So basically, if we are using this particular sequence, then we can easily say that finish of I equal to true for all I, and there is no case of any deadlock here. Now consider a second situation here. What is happening? Process P2 is requesting an additional instance of type C. Now just see here, the earlier process P2's request was 0, It means it hasn't requested anything at all. Now after some time, in the second case, not after some time, in the second scenario, what we are having here, process P2 request an instance of type C. So we are modifying the request matrix of process P2 by 0, 0, 1. Now see, currently we don't have any available resources. We don't have any resources in our disposal at this point of time. So now earlier P0 and P2 was there having they don't have any future requests, but now P2 is asking for one more resource here. That means we can only finish the process P0 without asking for any more resource. In the second case, what is happening? After P0 finishes its task, it will release its allocated resources into the system. So what is happening here is that the state of the system will be modified somewhat, can reclaim the resources which are held by process P0, but insufficient resources to fulfill other process requests. Now see here, if you finish the process P0, then then how the particular resources will change? We will be having only one instance of resource B available to us. But if you see the request of the other processes, say for example P1, P2, P3, and P4, we will not be able to satisfy any of those requests because we have only one instance of resource class B available to us. That means now what will happen is that a deadlock will exist consisting of processes P1, P2, P3, and P4. So in this way, a deadlock is being created in the system, and we have to detect it and recover it. So in this way, the particular detection algorithm will be working. Now, the thing is that when or how often you will invoke the detection of deadlock algorithm in practice. So basically, there are some issues here. How often a deadlock is likely to occur in the system, and if a particular deadlock ultimately happens, then how many processes are to be rolled back? So this is a particular issue that needs to be taken care of. And one more thing, if you are invoking the detection algorithm randomly at any point of time, then there may be the occurrence of several cycles in the resource graph. And if that happens, then we would not be able to tell exactly which are the processes which are causing the deadlock in the system. So that is the thing here. And ultimately, how to recover from the deadlock. If a deadlock ultimately happens, then what you can do, you can abort all the deadlock processes. That is one option available to you. Or then you can abort one process at a time and until the deadlock cycle is eliminated. Now in the second case, that is somewhat more costly. That means you have to invoke the deadlock detection algorithm after quitting each of the processes in the system. That will be a huge task. And thirdly, in which order should we choose to abort the particular processes? That means when we are about to abort some processes, in which order we have to choose them. It can depend on the priority of the processes, or how long the process has computed and how much more longer time it will take to complete, or what are the resources that a particular block process is been using till now, or what are the resources that a particular block process will need in future, or is the process interactive of a kind or a batch of a kind. So those are the issues that you have to take care of. And when we are and another case can be resource preemption. That means from a particular process you are forcibly taking away its resources. That means ultimately that process cannot continue with its execution, and you are reclaiming some resources forcefully to be allocated to some other block processes. So here, selecting a victim is a thing that needs to be taken care of. That means we have to select a victim in such a manner that it will result in minimal amount of cost. Or the second option can be rollback. That means a particular process can be returned to a safe state from where it can be restarted later on. And lastly, the thing is that when you are selecting a victim, it may happen that the same process is being victimized multiple number of times. So the number of rollbacks that a particular process is having to deal with can be included in its cost factor to be chosen as a candidate for deadlock. So these are the various recovery measures that you can adopt to recover from a particular deadlock.